Hello everyone, I'm Xiangyu Liu from Shanghai Jiao Tong University. Our paper's topic is tightly secure Chameleon hash functions in the multi-user setting and their applications. Okay, let's start from Chameleon hash functions, or CHF for short. Chameleon hash function is a special hash function indexed by a hash key, HK, which is associated with a trapdoor TD in the key-gene algorithm. It has two parts of input, message M and randomness R. On the one hand, given the hash key only, which means no trapdoor, it's hard to find the collision. On the other hand, one can easily find collisions with the help of the trapdoor, namely by the trapdoor collision algorithm. Here, a collision means that two different inputs lead to a same hash value. Formally, Chameleon hash function needs to have property of collision resistance or strong collision resistance. The first one states that for any probabilistic polynomial time adversary, it's hard to find the collision such that M1 is not equal to M2, while the strong collision resistance says that it's hard to find the collision such that the pair M1 R1 is not equal to the pair M2 R2. Besides this, Chameleon hash functions are required to have random trapdoor collision property. Usually, this property is necessary in the security proof. Chameleon hash functions are introduced by Cryptography and Rabin in 1998. For decades, numerous constructions of Chameleon hash functions are proposed. For example, CHF from the cloud-free permutation, CHF from the factual assumption by Chameleon and Twinman, CHF from the RSA-NN assumption, and CHF from the very smooth hash. In 2014, Blair and Ristovo proved that Chameleon hash functions and sigma protocols are equivalent. Due to this equivalence, many new Chameleon hash functions are obtained from well-studied sigma protocols like the Micheli-Shamir protocol and the Okamoto protocol. Well, although these constructions are probably secure based on proper assumptions, most of them consider single-user setting only. The question is, can these Chameleon hash functions achieve tight collision resistance in the multi-user setting? First, we need to define tight security of Chameleon hash functions. Usually, in provable security, we construct a cryptographic scheme S based on some hard problem P. Once there exists an adversary A that successfully attacks S with probability epsilon, we can construct another algorithm B that uses its ability to solve the problem P with successful probability epsilon prime. Since we assume that P is hard, namely, there is no efficient algorithm to solve it. Hence, such adversary A does not exist. Here, B and A have roughly the same running time, and we define epsilon over epsilon prime the security loss in the reduction. Well, let's take signature for example. In the single-user setting, the hard problem P is embedded into the user's key pair, verification key VK and signing key SK. The adversary A has a signing oracle that takes message M as input and outputs a signature sigma. At last, if it successfully generates a new forge M star sigma star, we can use this forge to solve the hard problem. However, most signature schemes are deployed in the multi-user setting. That is, there are many users at most, and each user UI has its own key pair BKI, SKI. Similarly, the adversary A has a signing oracle. The difference is that in the forge phrase, it wins as long as it can output a new forge M star sigma star for user I star of its own choice. Here, the security loss is defined by epsilon over epsilon prime. Tight security means that the security loss is a constant, not depends on mu. Actually, we can guess I star first and embed problem P into user I star's P pair. And if A chooses I star as its target, then we can finish the reduction like that in the single user setting. But this happens with probability 1 over mu. Consequently, with such hybrid argument, the reduction is loose, with the security loss at least mu. Well, in many cases, mu can be as large as 2 to 30. As a result, the development of the scheme has the deployment of the scheme has to be equipped with large security parameter to compensate the security loss factor. And that leads to large elements and slower computation. On the contrary, to achieve the same security level, tightly secure schemes have smaller elements, lower bandwidth, and faster computations. In consideration of wide applications of Chameleon hash functions, it's desirable for us to exploit tight collision resistance for Chameleon hash functions. Well, in this paper, we define multi-user collision resistance of Chameleon hash functions. That is, give mu random key pairs, HKI, TDI generated from keygene algorithm. It's hard to find I star and M1R1, M2R2 such that M1R1 cleaves to M2R2 under HKI star. Here we require M1 is not equal to M2. Similarly, we can define strong multi-user collision resistance, where the adversary needs to find the collision of two different pairs, M1R1 and M2R2. Okay, it's worth mentioning that not all constructions achieve tight security in the multi-user setting. We believe that most of Chameleon hash functions mentioned above, like CHF clone, CHF ST, and CHF RSAN, are hard to achieve tight security. But we identify three Chameleon hash functions, CHF DL from the discrete logarithm assumption, CHF RSA from the RSA assumption, and CHF factoring from the factoring assumption, and prove their tight, strong multi-user collision resistance security. Intuitively, the DL problem and RSA problem are random self-reducible. That is, given one DL problem instance, G to X, or RSA instance X to E, we can create multiple instances, G to Xi, or Xi to E, so that the DL problem and the RSA problem can be embedded into hash keys of all users. As for CHF factoring, we embed the factoring problem instance into the public parameter, which is shared by all users. In this way, no matter which target hash key is chosen by the adversary, the collision can be used to solve the factoring problem. That's why tight SMUCR security can be achieved. Okay, this is a construction of CHF-DL from the discrete logarithm assumption. This is the CHF RSA from the RSA assumption. And this is the CHF factoring from the factoring assumption. Okay, now we give some applications of our tightly secure Chameleon hash functions. Since all applications here are signatures, we first recall the definition of signature and its security notion. In the single-user setting, a basic security requirement for signature is essential unforgeability under chosen message attacks. It means that for a PPT adversary, it's hard to forge a valid pair, M star sigma star for new message, M star. A stronger notion, SUFCMA, states that it's hard to forge a new valid pair, M star sigma star. While in the multi-user setting, MUUFCMA says that it's hard to forge a valid message signature pair for new message, under VKI star, which is of A's own choice. And the strong multi-user UFCMA security defense in the similar way. By using our tightly secure Chameleon hash functions like CHF-DL, CHF-RSA, and CHF factoring, it's possible for us to get a variety of signatures with tight security. First, we extend the GBSW transform to the multi-user setting with the help of tightly SMUCR security Chameleon hash functions. The extended GBSW transform lifts a signature from unforgeability to strong unforgeability in the multi-user setting. The resulting strong multi-user EUFCMA secure signature can be used in group signatures, CCA secure encryption systems, and so on. Furthermore, we can cope with corruptions through the double key mechanism and get a tightly strong multi-user UFCMA secure signature against adaptive corruptions, which can be used in authenticated key exchange protocols. Our tightly MUCR secure Chameleon hash functions can further be used in multi-user online-offline signatures, Chameleon signatures, and proxy signatures. All these transforms fall in the hash sign switch paradigm, and the security is tightly reduced to the tight security of Chameleon hash functions and signatures in the multi-user setting. This is the first application of tightly secure Chameleon hash functions, extended GBSW transform. It strengthens signature schemes from weak unforgeability to strong unforgeability in the multi-user setting and enjoys a tight security reduction. Online-offline signature is a special kind of signature. It divides the signing algorithm into two phases, offline phrase and online phrase. Offline phrase can be viewed as per commutation, and it takes signing key as input only. Whenever there is a real message M to be signed, online phrase outputs the final signature, sigma. The online phrase is typically very fast, and hints can be executed efficiently even on a weak processor. Traditional signature schemes allow any part checking the validity of M and sigma. In some applications, M may contain sensitive information. Thus, it's viable for the signer to generate a non-transfer signature to the recipient. To this end, Cryptography and Rabbit introduced the concept of Chameleon hash signature to achieve non-transferability. This picture shows how to get a Chameleon signature scheme from a Chameleon hash function and a traditional signature scheme. The original signer signs for the hash value of message M and random R to generate sigma, and sends sigma R to the recipient, user J. Now it's hard for user J to convince a third party the validity of M, sigma, and R, because user J has the trapdoor. That is, it can find collision easily. Chameleon signature naturally implies a proxy signature. The proxy signature first gets sigma R prime for some random M prime and R prime. Upon receiving the real message M to be signed, it finds a collision using the trapdoor. Most of these applications fall in the hash sign switch paradigm. That is, there are two key pairs in the system, VK-SK for signature scheme and HK-TD for Chameleon hash function. In the first place, a signature sigma is generated for random M prime and R prime. Next, in the second phrase, given the real message M to be signed, a collision is found with the help of trapdoor, and the final signature is sigma R. Which party generates and keeps HK-TD depends on the needs of applications. With the help of tightly MUCR secure Chameleon hash functions, we can get tightly secure online-offline signatures, Chameleon signatures, and proxy signature systems. Okay, let's draw a conclusion. In this paper, we define the security notion of strong collision resistance for Chameleon hash functions in the multi-user setting and present three constructions: CHF-DL, CHF-RSA, and CHF factoring, and prove their strong multi-user collision resistance based on the discrete logarithm, RSA, and factoring assumptions. In applications, we first extend the generic GBSW transform to the multi-user setting, resulting in tightly strong multi-user UFCMA secure signatures. Furthermore, the extension can also be used to online-offline signatures, Chameleon signatures, and proxy signatures, and help us to get tightly secure signature schemes, which are widely used in grid computing, e-currency, electronic currency systems, and so on. Okay, that's all. Thank you.